So efficiency, again, a reminder, even though it says Physics 11, I'm doing the Physics 11 work unit with you, but you can call it Physics 12 if you want to. Efficiency basically means how much bang you get for the buck. That's an expression. Efficiency is how much of the energy that we put into a task is actually used to accomplish the task, and how much of the energy is wasted. Goes into other forms, as usually heat is the big one. Okay? There is a symbol for efficiency. It's this. It's sort of like a lowercase n with a droopy tail on the long part. This is actually the Greek letter eta. I didn't know that was the symbol for efficiency until just a few years ago. I always just wrote EFF. That was my abbreviation for efficiency. And so you may see in my answer keys or in my older notes, Diego, that I've written EFF. I don't care which one you use, but I know, hey, some students like to pull out the Greek because it makes them feel nerdy and important and smart. So that's good. Okay. What are the units? Typically, it's a percent. And I'll give you a basic one that you can do in your head. Let's suppose that to run a motor, I supply 1,000 joules of energy, but the work that we get out is only 500 joules of work. If I supply 1,000, but I only get out 500, anyone want to guess how efficient that motor is? 50%. Yeah. And so as an equation, well, it's work out divided by work in, or energy out divided by energy in, or power out divided by power in. What do you think? Am I going to actually make you memorize three? First of all, did I put this equation on your formula sheet? I can't remember. I used to not, but I've mellowed.
There's power out.
Okay. Here's Mr. Dewick's easier version of the equation. First thing, I have to match units. I have to divide watts by watts or joules by joules. I can't divide joules by watts. But my easier version is, it's always going to be the smaller number divided by the bigger number. You're always going to be less than 100% efficient. You can't be more than 100% efficient, because then what you're actually getting is free energy from nothing. Now, if you do ever manage to invent something that is more than 100% efficient, first of all, you will have violated the law of physics. It's called a perpetual motion machine, if you've heard that expression, or a free energy machine, if you've heard that expression. If we did have that, though, within about 5 years, you'd be richer than Bill Gates and Jeff Bezos. You could do whatever. Because if you give me free energy, even with our current level of technology, Elias, we can solve most of the world's challenges right now if we have an unlimited free energy. It would certainly take care of much of the climate change fossil fuel issues. We need to grow more food, got free energy. We can build sun lamps and we can run the lamps all night and double our food production. If you give me free energy, we can do an awful lot. But the universe steps in and says, no, you don't get free energy. The reason I'm saying that is normally, I don't think I'll get to it this year, but normally in your future, about a month from now, which we're not going to get to, there would be a question where many of you would be tempted to tell me that a light bulb was 140% efficient. And the reason, it's not. The reason is, when it comes to electricity, it's a bit tricky with our English, because if you're looking at a light bulb, the power in comes from an outlet. And so it's very easy to get power in and power out mixed up. So I wrote down here, efficiency is always less than 100% unless you plan on winning a Nobel Prize. This will give you a decimal. How do you change the decimal into a percentage? In other words, if you get 17 out of 20 on a test, how do you figure out what percent that is? You go 17 divided by 20, and then what? Okay, so for next to both of these, can you add times 100% times 100%? Now, I'll be honest, I almost always just do that in my head. I can glance at a decimal and convert it to a percentage in my brain because I've done it a bunch. But if you feel like you absolutely must have the calculator displaying the answer that you're going to write down, times by 100. Some examples. A typical household light bulb transforms energy at a rate of 60 watts, 60 joules every second. Most of the electrical energy, however, for the old incandescent bulbs, remember the ones that got really, really hot? Those ones. Most of the energy is turned into heat and not light, which is why we're slowly moving to LEDs. They're much more energy efficient. About 57 watts of power is heat. Only about 3 watts of power of light come from an old style incandescent bulb. You've all still remember those light bulbs. Yeah, you're not that young yet. You might still have those in your house, but I'm willing to bet most of you also now have some LED bulbs in your house as well, right? And you notice they don't get hot. They get warm, but certainly not burn your fingers hot. In fact, some of you might recall there were toys based on that. The Easy Bake Oven, all that was a glorified, I think it was a 140 watt light bulb in there throwing out a lot of heat, and you could bake some stuff with it. A kettle might transform electrical energy into heat at a rate of 1,500 watts. The power rating on an appliance is usually printed somewhere on the appliance, but basically the rule of thumb is the more heat an appliance moves around, the higher its wattage. Example 1. A 255 kilogram mass is being lifted, I'm going to underline the word lifted, straight up at a constant speed by an electric motor. I would probably notice the constant speed because often that allowed us to make some assumptions as well, yes? It takes the motor 4 seconds to lift the mass to a height of 12.5 meters. Okay, cool. Diego, what does A want me to find?
Find the work done.
Work equals, from your formula sheet, what times what? So we're in the work energy section. Don't feel bad. By the way, I'm also going to start nudging you to look at your sheets so you know where we're looking now. Okay? I know, it's after spring break. So beneath the force equations, I think it's the next group of equations, I think. So it should say W equals what? You're right. Yep. And then do you remember we made a more specific version of this? We said when you're lifting something, what was the equation for lifting something, the amount of work? Alec? Because the force that you're resisting is gravity, and let's call it height. If you want to, you could add a little subscripted lift next to work if you wanted to. And then let's do our quick check, Diego. Did they give me the mass?
Yeah.
Yeah. Do I know G? 9.8. Did they give me the height?
Yeah.
We're good to go. 255 kilograms times 9.8. 255 kilograms, that's about 700 pounds. So this is a heavy load we're lifting here, okay? And 12.5 meters, about 3 stories, roughly. 3.5 stories. So maybe we're lifting a piano up to the 3rd story of a building, of an apartment or something like that, because we can't get it in the elevator. What do you get? It's going to be fairly big. That seems about right. 31,237.5. I'll write down the whole thing and then I'll round off. 31,237.5, and then I'll say 31,200. What were the units for work? Joules. Okay. Diego, let's keep going. What does B want me to find?
The required power.
What was the equation for power? Probably right next to or right below the work equation, I hope, if I laid this out with any kind of organization.
P equals FGH.
No, that's PE, that's potential energy, not P by itself. And yes, we're running out of letters. So there should be a P all by itself equation, I hope.
No, P equals W.
What does W stand for? Work over.
Over time.
Yep, there we go. Do we know the work? We just figured it out, yes? Do we know the time?
Yes.
Well, then we're good to go. So it's going to be 31,237.5 divided by 4. And I get 7809.375. I'll write that down, and then I'll round off to 7,810. Power is measured in watt? Watts. Okay. C. Diego, what does C want me to find? Find its efficiency. Okay, and it says this. If the motor is using 12 what? Watts. So I'm not going to use the work over work because the units have to match. I'm going to use efficiency is power out divided by power in times 100. In other words, I'm not going to use the 31,237. I'm going to use the 7,809 because this is watts and I better use watts. My units have to match. So 12 kilowatts. How many watts is 12 kilowatts? Can you convert kilos in your head? Sorry? What's a kilo? How many? What's 12 kilowatts? This is one, because you're getting your driver's licenses soon, you might want to know that kilo is 1,000, because 1,000 meters, the road signs sometimes will give you distances to exits in meters, sometimes in kilometers. So 12 kilowatts is 12,000 watts. So how much power is the motor using? 12,000. How much are we getting out? 7,809.7. And so this is going to be on the top, and this is a bit easier to figure out which one is input, which one is output. But if I wasn't sure, the smaller number goes on the top. So it's going to be 7,809.375 divided by 12,000 times 100 to make it a percent. I can use my answer button, I think. And we get 65.1% efficient. Just seeing that number there, I know enough to know that this is almost certainly an electric motor, because gasoline motors are terribly inefficient. Gasoline motors are terribly inefficient. Those of you that have worked on a car engine or a gas engine, do they give off a lot of heat? Do they get fairly hot? Hot enough that you can't touch it? Okay, that's wasted energy. Can you hear a car engine from a long distance away? Sound is wasted energy, okay? So one of the reasons that hybrids are so much more efficient is just because your main source of propulsion is a more efficient engine. It's an electrical engine. Even though there's still a generator creating electricity from gasoline in hybrids, the power source of the car itself electrical engines are way more efficient. They don't give off much heat at all. They give off some noise, but not much at all. Example 2. A girl pushes a 3 times 10 to the 2. You know what? 3 times 10 to the 2, I'm pretty sure, is 300. Newton box along the floor for a distance of 4 meters. The coefficient of kinetic friction is 0.33. Hey, this is good review. I might even need to do a free body diagram. She then lifts the box straight up 1.2 meters. A says, what is the minimum amount of work she has done? Okay. I think the total amount of work that she has done, Calvin, I think it's going to be the work she does while pushing and the work she does while lifting. Looking at this question. Does that make sense? Okay. Calvin, work is what times what? So I think the work done by pushing is going to be the force pushing times distance. And what's the work done by lifting? MGH. And it's worth maybe on your purple sheet adding W lift equals MGH. I think I said do that yesterday, but if you were away yesterday, it might be worth doing today, or if you didn't do it yesterday. Okay. Are there any of these that I don't know, Calvin, my friend? Ah. You know what this might be a good job for? There's the box. What are the forces acting on it? Get the obvious one. What else? And I think same size as mg. I don't see any indication of angles or extra things at all. What else? Which way? Okay. What else? Yeah, you know what? Normally I'd call it F applied, but what did I call it in the equation? Not F applied, but sure. That's got to be what it is. I don't know F push. Or do I? Oh, but look. I think, assuming she's pushing at a constant speed, I know another force that has to be the same size as F push. Calvin, which force has to be the same size as F push? Yeah, this is why I said minimum. It's possible that she could be accelerating the box. She might be doing more work if she was accelerating the box, but let's assume she's a teenager. She's doing the minimum amount of, oh, sorry, that came out wrong. Or did it? Okay, so you got the little assumptions we're making here. So we're going to argue that we can turn this into work total is going to be the force of friction times this. Oh, there was a condition, Calvin, with this equation. The force and the distance had to be in the same direction. Now, is F push in the same direction as the distance that it's moving? Yes. So we can use this equation. I'm going to plug the magnitude of friction in, but it's pushing forwards, okay? Plus MGH. Friction is what times what? I don't know the normal force. Oh, but look, I know another force the same size as a normal force. So I think I can turn this into mu mg. There's friction. Distance, this is the horizontal distance that we're sliding. And then there's the work done lifting it up at the end. MGH. Did I give you a whole page? Okay, I don't need to write small. Sorry, I'm gonna go down another line and write bigger because at the back you folks are squinting. I reformatted this. I used to only have half a page and I'm writing small, but I reformatted this over the break to give myself more room. So let's do it large. It's going to be mu m g d plus m g h. Calvin, I've scrolled down, but can you tell me the numbers, please? What's mu? I don't know what's mu with you. What was the mass? Oh, it gives you mg because it's newtons. Well, so I don't even need to go times 9.8. I can just put the 300 right here. That is mg. Well, that's convenient. By the way, what's another word for mg? Starts with the letter W.
Weight.
Yeah, they gave me the weight, not the mass. Okay. Distance, how far did we slide it? Plus. And I can do the same thing here. Instead of bothering to find the mass, mg is just 300. What was the height we lifted it? I might be able to do this in my head. 300 times 1.2 is going to be 300 plus 60. It's going to be 360. File that away. It's going to be 1200 times 3. It's going to be 400. 760? Double check me. It's going to be yeah, sorry. I treated this as 1/3. I didn't round off. I'll get it to 2 sig figs. What is it exactly? I probably want this on my calculator, so I may as well do it. 0.33 times 300 times 4 plus 300 times 1.2. And here's the nice thing. Because work and energy is a scalar, even though these two distances are completely different directions, in Unit 1, I would have screamed at you. I would have said, how dare you put a horizontal and a vertical into the same equation? We're in scalar land. Who cares? That's one of the nice things about work and energy. 756? That we said? Units for work, Calvin? Good. Okay. Cool. AJ, what's B want me to find? Oh, efficiency, which is that funky symbol there. Okay. It says, if she expends or uses, I got both words in there, I need to delete one of them, 1,200 joules of energy while doing this, how efficient is this process? Am I going to go 1,200 divided by 756, or am I going to go 756 divided by 1,200? Okay. And then times 100 to turn it into a percentage. You get 63. Okay. Now, what does this mean? It means the amount of food energy this girl used in pushing was 1,200 joules of food energy that came out of her body. But only 756 of those joules went into moving the object. Where did the rest go? Heat. Her body probably gave off some heat. As she slid it across the floor, friction would have generated some heat. That's where the vast majority of it went. We're not very efficient creatures. We give off an awful lot of wasted heat. Okay. Example 3. On a stair climber at the gym. How many of you have ever used a stair climber before? Okay? Okay. So let's look at the physics of those, and you're going to hear me go on a bit of a rant here. A 58 kilogram person lifts their center of mass up 18 centimeters. Stop. I'm going to cross out the 18 centimeters. What am I going to replace 18 centimeters with? More specific. 18 centimeters is how many meters? 18 centimeters is 1.8 meters. You folks need to play with meter sticks a bit more and look at the numbers on them. 0.18, right? Okay. So a 58 kilogram person lifts their center of mass up 0.18 meters with each step. If they take 500 steps in 10 minutes, stop. Cross out 10 minutes. What am I going to replace that with? How would I convert 10 minutes to seconds? So I'm going to do that in my head, Sarah. 60 times 10, how many seconds? Okay. And I've showed you that trick of when I see yucky units, I just cross them out in the question, fix them there, and then I know I've got them fixed, right? And their muscles are 20% efficient. Okay, here we go. Austin, what does A want me to find? The rate at which the person does work. It's not asking me to find work. It's asking me to find the rate at which the person does work. What the heck is that? Nope. Everybody look up. From yesterday. Power is the rate at which work is being done. Okay? So, and I did that on purpose just to remind you of the official definition of power. It's how fast you're doing work. A is asking me to find, Austin, power. What's my equation for power? Good. I didn't underline a certain word in this question. I could have. What word should I have mentally underlined in this question? Yeah? Lifts. So, Austin, what's the work done in lifting? How do I calculate that? Yes. Do a quick double check. Did they give me the mass? Did they give me G? I know that. Did they give me the height? Did they give me the time? Okay, I think we're good to go. Austin, what's the mass? Good. G is 9.8. What's the height? I'm going to give you a hint. It's not 0.18. Now read the question carefully and tell me what else I have to factor in. Sorry? You're right. So I think the height is 500 times 0.18. That's the total height this person went through. Yes? 500 steps. Time? Good. How many watts of power? Do you get 85.26?
Yep.
Power is measured in watt? Not even enough to power a 100 watt light bulb. Okay. Austin, what does B want me to find? This is also power. What power? So now I'm going to make a little note here. I think the power that we got out is 85.26 watts. I think B wants me to find the power that this person put in from their body. Got the argument? What else have I not used yet? And the efficiency is not 20%, 0.2 when I turn it back to a decimal. I think, Austin, we're going to use this idea that efficiency is the power that we get out divided by the power that we put in. or the work that we get out divided by the work that we put in, but in this case, it's watts over watts. What was your question? That was a good question.
We're just talking about, I think it would be like the 85,
Probably.
20%.
I don't know. Let's find out. What am I trying to get by itself? Power in. Where is power in right now? On the... Yeah. Oh, wait a minute. We did this a little bit yesterday, too. I think I can multiply the power into the top over there, and at the same time, I can divide the efficiency to there. And so I'll end up with the power that this person put in is power out divided by 0.2. And yes, dividing by 0.2, it turns out, is the same as multiplying by 5. So you were correct. $426.3 watts. Okay? In other words, this is what, how many, so those of you that have used an exercise machine, how many of you have ever used the little calorie counter, little display thing? And please understand, that's complete garbage. That's complete garbage. The only way that they could give you an accurate count of how many calories is, first of all, they would have to know your mass. Do you have to enter your mass into these machines in kilograms? The higher end ones you do, but most of the time no. But the other thing is they would have to know your efficiency of your specific body, how efficient your body is at turning food energy into work. So whenever you see those calorie counters, they're wild guesses. You know what? They're ALEC voting. That's what they are. Okay? I mean, he's got a 1 in 4 chance of being right. So I can't claim that it's complete nonsense. But basically, those calorie counters on those machines are. They don't know what your body's metabolism is like. They don't know how efficient you are. But the other thing is, what it usually means is the amount of exercise. So this is power. If I wanted to convert it back to energy, I would just use the top part. That's how much energy, how much work you did. Your body actually did more because you burned a lot of heat. You gave off a lot of heat. So the other point is exercise is really beneficial. Even a small amount has a bigger effect than you realize. It's good for your body. Okay. Let's look at internal combustion engines, a gas engine. They're around 18% efficient. Only roughly 1/5 of the gasoline actually goes into making the car go. The other 80% wasted. So if a 200 horsepower engine is used for 2 hours, okay, clearly I'm going to convert 2 hours to time, and I'm going to convert horsepower to watts. I can't quite fit that in my little cross-out method up there, so I'll do it down here. So first thing, A says, how many watts is this motor rated for? Well, how many horsepower is this motor rated for? I'll write down what they gave me. And then I'll multiply. Hey, remember Physics 11? I want horsepower to cancel. Where will I put it? I'll leave that on. We'll see if YouTube picks that up. See if I get any comments there, Chief. Okay? I don't know if the microphone would have picked that up, but whatever. Where's horsepower going to go in my conversion factor? Bottom. And I guess watts goes there, and it's 750 watts is one. And this is how I know, oh, I multiply because the 750 is on the top. If the 750 was on the bottom, I would divide. Right? So it's going to be 200 times 750. I can do this in my head. 2 times 750 would be 1,500. So I'll add 2 zeros. Is it 150,000, I think? Yeah. Okay. So a 200 horsepower motor, which is a fairly big motor. Most 4 cylinders are less than 200 horsepower. In fact, some of them are less than 100 horsepower. So it's a fairly big motor. It's about 150,000 watts. B. What does B want me to find? Alec, what does B want me to find? How much motion energy does it produce in that time? What did I find in A? Power? What do I measure energy in? Joules. In the power equation, is there something in joules in the power? You know what? I think I'm going to go like this. Power is work over time. I think I'm going to get the W by itself, because that's the motion energy. That's the work that the motor is doing. How would I get the W by itself? Okay. So it's going to be 150,000. How much time? How'd you get that? Okay. 2 hours times 60 minutes times 60 seconds. I think last year some of you might even have memorized that 1 hour is 3,600 seconds. You could get there in one quick step. So, how much gasoline energy is going into moving this car? You get 108 and then 7. You know what? Let's write this in scientific notation, I think. Okay. I'm going to go 1.08 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 10? 1, 2, 3, 4, 5, 6. You're correct. Mr. Dewitt can't count. Joules. Okay. C, how much energy is wasted? What haven't I used yet from this question? Efficiency. So I think I'm going to go efficiency is work out divided by work in. The question is this how much work we got out, or is this how much work we got in? Yeah. So you're saying it's going to go here? Okay. And that's where these can be kind of tricky. But I do know that I can't get an answer bigger than 100% efficient. So how am I going to do this? Let's see. I think it's going to end up being what's the efficiency? 18%? Yeah. Sorry, 0.18 equals, I think this is how much fuel energy that we burned. This is how much we actually got out. Okay. Most of that energy went into heat and sound. How would I get the W out by itself? How will I move that 1.08 times 10 to the 9th over? Multiply? Sorry? Okay, so we'll get the amount of work that we got out was equal to 0.18 times 10 times 1.08 times 10 to the 9th. So I'll take this number, I'll multiply it by 0.18. So that's how much we got out. If you want to know how much we wasted, we started with 1.08 times 10 to the 9th minus what went into moving the car, and that's how much energy was wasted. Gasoline engines are really not a good deal. They're really not. So why do we use them? Well, we haven't found a replacement for. One thing gasoline, fossil fuels are very good at is containing a large amount of energy in a small usable source. The amount of energy per liter of gasoline is staggering. So it's really easy to fill up your tank and go a long way. Compare that with, say, the amount of batteries you need in a Tesla to get 400 kilometers is huge compared to the size of a gasoline tank. So we're working on it. So anyways, if you're looking for the answer to this, it was 1.944 times 10 to the 8th. And so the wasted energy would be 1.08 times 10 to the 9th, what you start with, minus what went actually into moving the car. And you get 8.856 times 10 to the 8th. Anybody here own or have their folks drive an electric vehicle? No one? Okay. I'm hoping by about 2030 or so that's when we'll start to realize, oh, there's more electrics. We're just waiting for the breakthrough in battery technology, and they're working on it. Okay, so efficiency. You can try number 1. You can try number 2. I'll skip number 3. You can try number 4. I skipped 3. You can try number 4. Five is good. 6 is good. 7 is good. 8. 9 is good. 10 is good. 11. And 12 is long. 13 is long, so you can skip 12 and 13. You can do 14. You can do 15. I'm going to give you about 15 minutes, but I do want to get a second lesson in if I can today, because otherwise we're not going to finish the course. So I apologize, but you have a long weekend coming up. Thursday, your homework is going to be a test, but you won't be taking much homework with you, so sorry.